Hey guys, today we'll be looking at series. So a series is a sum of the terms in a sequence. So what do we mean by a sequence? A sequence is just a list, an ordered list of items that follow a certain pattern. So we could have a sequence of the natural numbers, and the pattern they follow is they go up by 1. Now if instead of writing this down as a list, if I write down the sum of all the terms in the sequence, this is now what is known as a series. So this is a series, and this is a sequence. So today we'll be looking at how to find the sum of different kinds of series and some useful notation known as sigma notation, which is this symbol, sigma, the Greek letter sigma, and what this means and how we can use it to write down series concisely and clearly. So let's begin with this notation. So this means the sum or the summation. So we may see it with a number at the bottom and something at the top. What this means is we start with r equal to 1 and then plug in successive values of r. So starting from r equals 1, then 2, 3, 4, 5, 6, all the way up to n. So r equals n is where we stop. So n tells us the last value r will take on. And to the right of this symbol over here, you'll probably see some constant, some variable, or an expression. Let's say we have a variable, the variable r here. What this means is we start with r equal to 1, so we plug in our starting value into this, r equals 1, and then add to it, because we're doing the sum, remember this symbol means the sum, add to it r equals 2, r equals 3, r equals 4, all the way up to r equal to n. So this sum right here is what this expression is a concise way of writing down. So let's look at some examples. Let's say we have from r equals 1 to 3, this would be the sum of 1 plus 2 plus 3, because we stop at r equal to 3. So this sum equals 6. So 6 is the value of this sum. Let's say we want to write down a sum of just constant terms. Maybe we want to write down the sum of 1 plus 1 plus 1 5 times. How would I write this down in sigma notation? This would be starting from r equals 1 to 5, because we've got 5 terms, and instead of writing a variable over here, we just write the number 1. So this expression means the sum starting from r equals 1 to 5 of just the constant 1. So we're adding 1 to itself 5 times. If I have this sum, for example, so the number 3 here instead, this just means 3 added to itself 10 times. So if you have a constant over here, this number just tells you how many times you're adding that constant to itself. Now let's look at some more complex sums. Let's say I have this expression. What this means is we start with r equal to 1 and we plug it into this expression and then plug in different values of r. So r equals 2, r equals 3 is our last value of r, and we do the sum over these. So let me show you what I mean by that. So plugging in r equal to 1, I have 10 times 1 minus 1 plus, now I'm going to do 10 times 2 minus 1 because we've moved on from r equals 1 to r equals 2. Then I'm going to add 10 times 3 minus 1 because that is the last value of r and that's where we stop. So evaluating this, we have 10 times 1 minus 1 is 9, 10 times 2 minus 1 is 19, 10 times 3 minus 1 is 29, so this equals 57. So the value of this sum is 57. Why this is useful is because say we want to find the sum of the first 100 natural numbers. So I want to add 1 plus 2 plus 3 plus 4 plus 5 all the way up to 100. Well, as you can see, I don't have enough time to sit down and write down this entire sum. So this sigma notation gives me a very concise way of writing down this really long sum in just a few symbols and numbers. So this looks like the sum from r equals 1 to 100 of r, and these two are equivalent. Let's actually find what this sum is. What is the sum of the first 100 natural numbers. How can we work it out? Well, there's actually a very clever way to do this without sitting down and adding 1 plus 2 plus 3. This method was first introduced by Gauss, who came up with a quick trick to find the sum of the first n natural numbers. And as the story goes, he was quite young when he figured this out. His maths teacher had asked the class to find the sum of the first 100 natural numbers, thinking it would take them quite a while, but Gauss gave the answer almost immediately. So let's see how he did it. He used this property known as the commutative property of numbers. What this means is numbers can be added in any order, but they will give the same answer. So 2 plus 3 is the same as 3 plus 2. This is the commutative property. Now let's use this to find the sum of a simpler example. So let's say we're finding the sum of the first 10 natural numbers. So I want to add up all the numbers from 1 to 10. What I'm going to do is write the sum twice. So I'm going to duplicate it and add this to this. So if I'm adding the same set of numbers twice, whatever this sum is, our answer, if we add this again, will just be twice the sum of the numbers from 1 to 10. So if I can find this sum and divide it by 2, then I'll have the sum of the numbers from 1 to 10. So let me expand the brackets and actually write down the sum. So this is the sum we are trying to evaluate, and whatever the answer is, I'll divide it by 2 in order to find the sum of numbers from 1 to 10. The reason why I've doubled it will make sense when I explain the method Gauss came up with. So he noticed that pairs of numbers, so here 10 plus 1 equals 11, 9 plus 2 equals 11, 8 plus 3 also equals 11, 7 plus 4 equals 11, 6 plus 5, and so on equals 11. So we've got here 10 pairs of numbers whose sum equals 11. So if I do 11 times 10, because we've got 10 pairs of numbers whose sum equals 11, if I do 11 times 10, then I have the sum of all the values in these brackets. So 11 times 10 is 110. So we need to divide our answer by 2 in order to have the sum of the first 10 natural numbers. So 110 divided by 2 is 55. So 55 is the sum of the numbers from 1 to 10. The way Gauss noticed this and the fact that he could use the commutative property was he essentially has rearranged these second brackets from going in an ascending order to going in a descending order. And then he noticed that the sum of these numbers were all the same. So a general expression for the sum of the first n natural numbers is a half times n plus 1, which is exactly what we did here. For the case of summing the first 10 natural numbers, we did a half times 10 times 11. So let's find the sum of the first 100 natural numbers. This will be a half times n, which is 100, times n plus 1, which is 101. So this gives us 5,050.